Hello, welcome to another day of physics, and not just any day, but the beginning of the end, the first day of the last chapter. Um, we're wrapping shit up. Before I get started, um, there will be a review session tomorrow. Tomorrow at noon, I'm going to go through last semester's final. That's the time that had the most votes for it. There was no time that everyone who signed up could do. That was the best I got. I will be recording it. I will be posting it to YouTube. So if you can't make it / don't want to make it, the video will be up. I'll also post the solution to last year's final after that. And keep in mind that your final exam is 1 week from today at 1 week plus 1 hour is exactly when it is. So a week from today at 3. So that's something to, I guess, look forward to. But that is up and coming. That we are at the end. Any questions about review and final and that type of stuff before I do, physics? Looks good. Okay, so this chapter, what we're ending with is energy in thermal processes. Basically, we're going to go back and talk about energy a little bit more, but how energy relates to temperature. The short version is energy flows from hot to cold. Those should be italicized T's, but they're not. That's the short version. If you have a hot thing and you have a cold thing and you put it together, hot will flow to cold. And the reason why it's a flow of energy. See, last chapter we talked about energy in thermodynamics, how anything at a given temperature has an amount of kinetic energy equal to 3/2 kT. And if you put two things together at different temperatures, energy will flow from the thing with more energy, aka the hotter temperature, to the thing with the colder temperature. This gets into the idea of heat. See, last chapter we talked about internal energy, where internal energy was 3/2 nkt. Internal energy is the total energy relating to temperature of the thing with the molecules moving inside. But this chapter, we're mostly going to talk instead about heat. Heat, which uses the symbol Q because is transfer of energy. See, if you remember back when we did chapter 5, we had kinetic energy was Ke and work W was change in kinetic energy. We're seeing thermodynamics, energy is still Ke. Total internal energy, though, is just U, because K is just one molecule, U is all the molecules. But heat, which is Q, is the change in thermal energy. Just like work was change in mechanical energy, heat is change in thermal energy. And so if you say you are heating something up, what you really mean is you're increasing its thermal energy. I mean, heat kind of has some other meanings in the real world, not physics, because of this. But heat is change in thermal energy. Once again, symbol is capital Q. Now, being that heat is change in thermal energy, it's a change in energy. It must have units of energy. Heat is always measured in joules, at least in this class. It is of note that it is not the only metric unit for heat. It is the SI unit for heat. But of note, calorie is also a metric unit, where 1 calorie is 4,186 joules. Fun fact for this is not the same calorie as what food is measured in. Okay, so this is just crazy. So food is measured in kilocalories. Well, 1 kilocalorie is 1,000 calories. But it sounds, if you say something has 1,000 calories versus 1 calorie, 1 calorie sounds better. But if you say 1,000, if you say 1 kilocalorie, that sounds pretty bad too. And so somehow the food industry got to measuring things in calories with a capital C. Well, a calorie spelled with a capital C is 1,000 calories with a lowercase c, because that's not confusing at all. So food is actually measured in kilocalories, not calories. They just call it calories and give it a capital C to make up for it. Marketing. Sorry, that's just is what it is. But a calorie is a unit of energy. If you're eating something and it says it has like 200 calories in it, or 200 kilocalories, what it means, that is saying how much energy you're putting in your body, energy that you can turn into movement, or in my case, just fat. Okay? But that is of note. Heat is a type of energy. When you heat something up, you are adding energy. And in fact, this is a usable thing. There's such a thing called a Stirling engine. This is a Stirling engine. What I have is my Stirling engine, and I'm trying to make this fit. We don't need those lines anymore. Is my Stirling engine, I'm going to put it on a hot plate. When I put the Stirling engine on a hot plate, that is going to increase temperature. Because it increases temperature, it's gaining internal energy. It has heat. And it's just the Stirling engine is something that turns thermal energy into mechanical energy. Because this is gaining energy due to temperature, that it's gaining energy because it is gaining heat, it causes mechanical energy. And it spins pretty fast too. Okay. Now, when you add heat to something, when you add heat to something, you can really do two different things with it. And I'm going to start with one, I'll come back to the other. But the main thing that happens when you add heat to an object is you increase its temperature. Because keep in mind, total internal energy, U, is just 3/2 NKT. And Q is just change in U. So if you add heat, you're either changing a constant or a different constant, and they're constants, you're not changing them, or number of molecules, but that's not what you're changing either, or the temperature. So it has to be. Anytime you add heat to something, or anytime you change the heat of something, I should say, you change the temperature. Q can be negative, but if Q is positive, you increase the temperature. If Q is negative, you decrease the temperature. You take away heat. And Q, if you want to find the amount of the temperature change, it goes by this equation. Q equals mc delta T. Now, first off, because it's a delta T equation, you can work in Celsius or Kelvin. M is the mass of the object, and C is what is called the specific heat. C, which if I rearrange, I could define differently. C is a constant for any given material. That simply says how easily it changes temperature. Things like metals have a very low value of C. It doesn't take much heat to change the temperature of metal. Insulators or water have very high specific heats because it's hard to change their temperature. But that's the equation. That the heat required is mc delta T. Delta T is always final temperature minus initial temperature. And once again, the bigger the value of C, the more heat it can store without changing in temperature, aka the more heat you need to change the temperature. Any questions so far? Okay. Here are some very specific heats, just so you have them. Something of note that's going to come up later on, but I want to fit a few notes. First off, water has a stupidly high specific heat. At room temperature, water is one of the highest specific heats. Water is very hard to change the temperature of. But what's more interesting is water, which is H2O, has this specific heat. Steam has this value. Ice has this value. Specific heat is mostly constant for a substance, but it does change with phases. Because the specific heat of ice, steam, and water, even though the OH2O are different, that's going to come up later on. However, moving on with this. So, Q is heat and change in thermal energy. But we also know the law of conservation of energy. Energy can't be created or destroyed. And therefore, in a full system, we cannot create energy. We cannot destroy energy. And so if there's change in energy and energy can't change, that means the total heat in any closed system must be zero. This can be used anytime you take a hot thing and a cold thing and put it together. Right now in my drink, you can kind of hear, I don't know if you can hear it, there's ice in here. You can't really hear it, but just trust me, there is. When I put ice in this water, what happens is the ice melts and warms up. the water gets colder. They both have a change in heat, but the total change in heat must be 0. Anytime you put two things together or more, you could do more. What will happen is if you put things together and give them enough time, they will go to thermal equilibrium. That the hot thing will give away heat and the cold thing will take heat so that the final temperature is the same using this whole Q equals MC delta T. And if you mix two things, you'll just say MC delta T of one thing plus MC delta T of the other thing, where T final is the same of both things. But if it is going to thermal equilibrium, that will be 0. That in the thermal equilibrium, and if it's, once again, if this is two things, we would say that Q1 plus Q2 must be 0. That that when you mix things, T final will be the same for both objects, but the total change in temperature or the total change in heat will always be 0. Any questions though? So I'm going to start with a simple problem, and then I'll get into the kind of things you normally are needing to solve. This idea, this Q equals 0, it is sometimes used in something called calorimetry. Calorimetry is you basically take an unknown substance and throw it in hot water. By taking an unknown substance and throwing it in hot water, you can find out what the substance is. And this is my first example. Let's say I have a 125 gram block of an unknown substance. Oh, sorry, I said hot water. You heat up the metal, not the thing normally. You heat up one thing. This one I heated up the block, not the water. And I heat this block of metal, I'll say it's metal, I'll say that much, to 90 degrees. And I put it in a styrofoam cup with 0.326 kilograms of water at 20 degrees. The system heats a thermal equilibrium of 22.4 degrees Celsius. I can use this to find out what the metal is. If nothing else, what its specific heat is. See, the reason I can do that is I know energy must be conserved. That means the total heat must be 0. And I have two things happening here. I have it's not aluminum. I have an unknown substance. I have an unknown substance at 90 degrees going to 22.4 degrees. I have water at 20 degrees going to 22.4 degrees. That the unknown substance is losing heat while the water gains heat. And the total heat must be 0. So heat of the water plus heat of the unknown, sounds like a bad action movie title, must be 0. Well, each one's heat change will be MC delta T. So I'll say M water, C water, T water final minus T water initial, plus M unknown, C unknown, T unknown final minus T unknown initial. And I can use this to find the specific heat of the unknown. See, I'll just subtract the water stuff from both sides. And I'm going to do something kind of interesting here. This is kind of a trick, but I think it's kind of nice, makes life easier. Is I have this negative sign. I'm going to just bring this negative sign in here. And so what that's going to do is it's going to reverse it. It's going to get rid of the negative sign. Instead of final minus initial, we'll make it initial minus final. That makes sense? Then I'm going to make some space. And I'll just divide both sides by everything that isn't C. And there you go. There's my unknown. This will be my value. If I know the specific heat of water, which I didn't write in the problem, but you can look it up. I always give it in the problem when you need it. And I can plug in. Now you'll note I kept two finals here. I don't know why I did that, but they both have the same final temperature. That is important. That's going to come up later on. I put in 22.4 for both. I just labeled them differently for some reason. 22.4 minus 20 is 2.4. 90 minus 22.4 is 67.6. Some kilograms cancel. Some C's cancel. I get a value. This unknown substance has a specific heat of 388 joules per kilogram degrees Celsius, which for the record, I can now look up and find out is copper. I know what it is. Any questions? Okay. The next one is a test problem and is more like what you expect on the exam. I'm going to be honest. On the exam, there will be a question like this next one or like something else I'm going to do today. I'll give more information after I do both. But more common, you know what the substances are. And more common, what you want to find is what is the final temperature. If I take this hot thing, mix it with this cold thing, what is the final temperature? That's going to be what you normally solve. This next one, as I said, is an old exam problem. It is way too wordy. I used to have a problem with making my problems too wordy, and I have since keep myself from writing this much shit, this much lore, I should say. But in Game of Thrones, Tywin Lannister has a sword made called Oathkeeper. I'm skipping most of this stuff here. How you make a weapon is you heat it up real hot, you shape it, and then you quench it in oil. Quenching means taking the hot sword into, actually, normally heated oil. You normally want the oil hotter than room temperature. It's to make it stronger. You could use water. Water will make it weaker, and if the oil is hotter, it will be stronger. So I looked up how to make a sword with Damascus steel, which is what people think the Valyrian steel of Game of Thrones was based off of. And let's say I take a sword and I heat it up to 816 degrees Celsius. And then I dunk it into 49-degree Celsius oil. If the sword weighs 4.31 kilograms and the oil has a mass of 9.2 kilograms, what is the final temperature of the sword in the oil? So there's my note. I have the mass of the oil, I have the mass of the sword. I have the specific heat of the oil, I have specific heat of the sword. And I have the initial temperature of both. And I say, what is the final temperature? Okay, we good here? Well, let's solve it. What I know is energy will be conserved. That means Q total is 0. And I have two things here, a sword and oil. So the heat of the sword plus the heat of the oil must be 0. Well, heat is MC delta T. I'm ignoring any oil that might evaporate in the process. We'll come back to that. So therefore, M oil C oil delta T oil plus M sword C sword delta T sword must be 0. And here's the thing. If you let this go to thermal equilibrium, both things will have the same final temperature. That T final for the oil will be the same as T final for the sword. And our goal is to solve for T final. Now, when you look at this, I've had people many a time say, but there's two T finals. Which one am I solving for? And the answer is yes. They're both the same. You don't solve for one or the other. We factor it out. I'm just going to rearrange this equation so I have T final equals. It's just algebra at this point. It's not the world's simplest algebra, but it's algebra you should know how to do, and I'm about to show you. But I'll rearrange and solve for the final temperature. What I'm going to do to get T final alone is I'm going to factor out both sides. I'm going to factor out the parentheses. Then instead of M oil, C oil, parentheses stuff, I'm going to do M oil, C oil times T final. M oil, C oil times negative T initial oil. And I'll factor them all out. When I factor them all out, what I have is two terms with a T final in them. And I have two terms without a T final in them. And I'm going to take everything without a T final and move it to the other side. That both these things I circled in blue, I'll add it to both sides of the equation. So I have the red on the left and the blue on the right. Now, if I look at my left side of the equation, these both have a T final in them. So I can factor that back out. And I can say T final is M oil C oil plus M sword C sword. And if I divide both sides by that shit in parentheses, There you go. Quick thing. On the exam, the problem will be either something like this or something involving a phase change. We're going to do phase change in a second. If it's something like this, and you jump directly to this equation and do not show the works to get here, I will not give full credit. You must show your work. If you jump straight to that, at best, I'll give you 5 points. At best. You must show your work. Okay? Let's plug in some numbers. I have all my numbers above. I'll throw them all in. And I'll just plug that into a calculator, and I'll get a value. That's the temperature it reaches. Any questions? Okay. If there's no questions, I'm going to make it a hell of a lot more complicated. So make sure you're still good with that before I go make it complicated. There's a slight issue with some of the stuff I said. You see, I said heat is mc delta T. But let's say you take a pot of water and you put it on a stove. When you put it on a stove, what you do is you add heat. The water gets hotter. But the water only gets so much hotter. Eventually, the water boils. And when the water boils, it doesn't just keep getting hotter, it boils. Hence yeah. You see, any substance, not just water, can also change phase. And a phase change occurs anytime we go from one type to another. Then if we go from a solid to a liquid, you melt. When you go from a liquid to a gas, you evaporate. When you go from a gas to a liquid, you condense. When you go from a liquid to a solid, you freeze. And you can always go the big jumps. Solid to gas is sublimation. Gas to solid is deposition. I'm never really going to talk about those. But it takes heat. To turn a solid into a liquid, it takes heat. To turn a liquid into a gas, it takes heat. And the other way releases heat. If a gas becomes a liquid, heat is released. If a liquid becomes a solid, heat is released. See, if I just talk about water boils at 100 degrees Celsius. If you heat water to 100 degrees Celsius and start boiling it, heat will be used to boil it. And see, that equation, Q equals mc delta T, assumes no phase change. If there is a phase change, you need another equation to talk about the heat required for the phase change. And the heat required in any phase change goes by Q equals Lm. In this equation, Q is the same old heat, M is the same old mass, but L is what is called the latent heat. It has units of joules per kilogram and simply talks about how hard it is to change the phase. Except to get more complicated, there's really actually 3 different values of L. See, for any material, and I'm going to use water as an example a lot, so H2O, there's 3 values. The latent heat of vaporization, the latent heat of fusion, and the latent heat of sublimation. We're going to ignore sublimation because we don't care about it. The latent heat of vaporization is going to be used anytime you go from a liquid to a vapor or a vapor to a liquid. Liquid to gas or gas to liquid. Vapor, gas, it kind of follows. Fusion will be anytime you go from solid to liquid or liquid to solid. But this says how much energy is required to change the phase. And this actually gets kind of interesting. It gets kind of complicated. Because let's say you got a block of ice and you got some really cold ice. It's less than 0 degrees. And you want to turn it to steam. If you want to turn ice to steam, you're going to have to do heat to change its temperature, but also going to have to add heat to change its phase. In fact, the heat required to change ice to steam will follow this set of equations. And that if you look at a block of ice and you block its temperature as a function of the heat you add, what you'll find is that the temperature will go up linearly for mc delta T while it's a solid. until you hit the melting point for water 0 degrees. Once you hit the melting point, you can't make it hotter. Instead of becoming hotter, it'll melt. And all heat you add would go towards melting. Q equals MLF. Once it's melted, then it can go up in temperature. Q equals MC delta T. And that'll continue until it boils. Once it boils, it's going to stop going up in temperature. And Q equals ML sub V, there will be the heat required to boil. Until it's all boiled, they can change the temperature of a gas. But the annoying thing is, for all substances, all of these constants are different. That this constant, and this constant are not the same. And this constant are not the same. And so if you want to find the heat required to change the temperature and the phase of something, you're going to have to use multiple pieces of this. So here's some values for latent heats. We're going to use joules per kilogram, but there's some values. Just want it up there. And I want to solve a problem. This problem is a little more, that didn't do something it was supposed to. This problem is a little more complicated or longer than something I put in an exam. It's simpler than something I put in an exam, but it takes longer, if that makes sense. But it's a good way to look at it. This is commonly called the marathon problem because it never fucking ends. And here's the idea. Let's say you have 25 grams of ice. This ice is at negative 20 degrees Celsius. How many joules does it take to turn it into steam at 110 degrees Celsius? Now, if it wasn't changing phase, we just say MEC delta T. Boom, done. But if it's changing phase, you're going to have to deal with that. You're going to have to say how much heat is required to change all the phases and the temperature. You see, if I'm going to say how much heat is required to go from negative 20 degrees Celsius to 110, that means I'm going from there to there on this graph. I'm going to have to find out how much heat is required to change the temperature of ice to the melting point. How much heat is required to melt the ice? How much heat is required to go from 0 to 100 for liquid? How much heat is required to boil the liquid? How much heat is required to go from 100 to 110 of the gas? I'm going to have to work out each piece step by step and then add them up. Any questions here?
So, Professor, if I wanted to move in the other direction and go cooling, can that be negative?
Okay, if you're going in the other direction in cooling, MC delta T will be negative. I didn't actually explicitly say this, but like the latent heat of fusion is will work for going solid to liquid or liquid to solid. Officially, it's negative going in the other direction. So if you wanted to go the other direction, you would just, your MC delta T would definitely be negative by default. Okay. And for this, you would just say it's negative, yes.
Okay. And just thinking out loud here for a second. So my instincts tell me that gas is generally a higher state of energy than a liquid.
That is true.
These flat lines are confusing me a little bit.
That is mid-phase change. So what this is like, okay, let's say you are making tea, right? You're boiling water on the stove. Mm-hmm. It's initially going to all be liquid. When it starts boiling, what happens is while it's boiling, some of it is still liquid, some of it is boiling away. Some is liquid, some is gas. Wait. Oh, my mouse disappeared. Come on, mouse. Come back. This region to this region is the boiling process. And it's not on this last region until there's no liquid left, that it's all gas.
But then between that region, we're saying there is a net energy exchange, aren't we?
Yes, there is a net energy exchange, and the energy is going to changing the phase, one molecule at a time.
Okay, I think I'm with you.
Okay, so let's solve this stupid problem. Come on, go. So here we go. I don't know why that didn't have a transition. If I want to solve this, I'll first say 0.025 kilograms of ice at negative 20, the steam at 110. I'll first say we have ice at negative 20, that ice is going to go to 0 degrees. It's only going to go to 0 degrees because that's the melting point of ice. And I'll say the heat required to make ice go from -20 to 0 is mc delta T. The mass of the water or the ice, the specific heat of ice, which is not the same as water, as I said earlier, times the change in temperature of ice, 0 minus -20. That says I now have ice at 0 degrees. Now that I have ice at 0 degrees, I can find how much heat is required to melt that ice. The heat required to melt that ice will just go as ml. It will be the mass of the ice times the latent heat of the ice. And this will be how much heat is required to go from ice at 0 degrees to water at 0 degrees. I now have water at 0 degrees. Now that I have water at 0 degrees, I can turn it to water at 100 degrees. To find how much heat is required to go from 0 to 100 degrees, that's a change in temperature. A change in temperature is an mc delta T, where you'll note my C value changed because it's a different thing. And I would say the amount of heat required to go from 0 degrees to 100 degrees would be the mass of the water, specific heat of the water, 100 minus 0. Now I have water at 100 degrees. My plan is to make it gas. If I want to make water into gas, I have to take my water at 100 degrees and turn it into steam at 100 degrees. And the amount of heat required to turn water to steam is Q equals ml. And so I can figure out exactly how much energy it takes to go from water at 100 degrees to steam at 100 degrees. And now I got a cloud of steam at 100 degrees, but I don't want a cloud of steam at 100 degrees. I want a cloud of steam at 110 degrees. So I can find how much heat is required to go from 100 degrees to 110 degrees. With the heat required to go from 100 to 110, Q equals mc delta T. Well, I use the mass of water, specific heat of steam, and 110 minus 100. And what these formulas did individually is the heat required to heat ice, the heat required to turn ice to water, the heat required to change the temperature of water, the heat required to boil the water, the heat required to change the temperature of the steam. And the heat required to make this cold ice into hot steam is just the sums. I'm just going to add these all up. Because if I add them all up, what I get is the heat required to do all of this, where I can get an answer. Questions? Okay, let's get more complicated then. Before I started this up, I had you figure out the final temperature of a soda and oil. And when I said Q total is 0, you can find the final temperature of something. This is also true when you have phase changes. If we heat a ball of, I'm pretty sure it's nickel, up to red hot, super, super, super hot, and take this ball of metal and drop it on a big hunk of ice, what it's going to do is it's going to melt the ice and heat the water. It's actually probably going to heat up the ice, then melt the ice, then heat up the water, at the same time cooling down the metal until we reach thermal equilibrium somewhere around there. But Q total is still 0. If you have a phase change, you can still say Q total is 0. You just have to include the unit, the bit for the phase change. On the exam, you will be given a hot thing and a cold thing, and you will be asked to find the final temperature. It might involve no phase change, like the sword, and it might involve a phase change, like the one I'm about to do. It will be one of these. This is part of the reason I'm okay with doing the review tomorrow, even though I won't be done with the chapter, because the stuff we do on Wednesday isn't going to be on the final. It is going to be this. Maybe with a phase change, maybe not. And so let's do a problem. I heavily researched to test this problem. Lots of research on this one. And I worked out that a 10-gram cube of ice at 0 degrees If you drop it into 96 grams of bourbon, which is 3 fingers worth of bourbon, at room temperature, which is 20 degrees Celsius, if I drop a 10-gram cube of ice at 0 degrees into 96 grams of bourbon at 20 degrees, what's the final temperature? This is an old exam problem, by the way. What I would do is I would say, first off, SI units. 10 grams of ice, 0.01 kilograms. 96 grams of bourbon, 0.096 grams. And I'll say the ice started at 0 degrees. The bourbon started at 20. And what I know is energy must be conserved. Energy cannot be created or destroyed. That means Q total is 0. The energy the bourbon lost plus the energy the ice gained must be 0. But let's talk about what happens here. You see, I was nice and started this ice at 0 degrees. Ice out of your freezer is going to be a little colder. And what that means is that the ice isn't just going to heat up. It's going to need to melt and become water. Once it becomes water, you have a mixture of bourbon and water, where the bourbon is still going to be hot and the water is still going to be cold. And they're still going to try to reach thermal equilibrium. So we have 3 heat things here. We have the ice melting. We have what once was ice is now water warming up. And we have bourbon cooling. So it's really Q bourbon plus Q melting plus Q water, where the water wasn't originally there, but it is now. Side note, this is getting ahead of myself, but the latent heat of fusion for water is super, super, super high, which is awesome. It's why ice is so good at cooling things. That like ice is real good at cooling things because it takes a lot of energy to melt ice. And that lot of energy to melt ice, it goes into cooling things. So, interesting fact. Now, for the bourbon and the water, that's a change in temperature, MC delta T. For the ice melting, that's a change in phase. And so what I'll say is total will have MC delta T of the bourbon plus ML for the ice plus MC delta T for the water. And for the record, I would give you the C and L values. I just didn't write them in this text. They'll come up as we need them. So, any questions as of now? Oh, here they are. There's the C and L values. Now, as I said, I was nice here. If the ice was colder than 0 degrees, you would also have a change in temperature of the ice. But I didn't. I said the temperature of ice initial was 0. So that term goes away. So it's actually just MC delta T for bourbon plus the change in temperature of the ice plus the change in temperature of what once was ice is now water. You'll notice I didn't do CI. I used CW. Because it's no longer ice. Once it melts, it becomes water. So I don't use specific heat of ice, I use the specific heat of water. Phase changes, that's what happens. So we'll take all this, put it aside, and say, okay, I want to solve for T final. But I have the same issue I did last time. I have 2 T finals. And so just like last time, I'm going to have to factor this out. I'll take my side with the parentheses and factor through. That MBCB T final minus TBI, I'll factor to be MBCB T final minus MBCB TB initial. And just like last time, I'm going to take everything with a T final in it and say, you're cool, stay here. Everything without a T final, get to the other side of the equation. I will add this to both sides of the equation. I will subtract this from both sides of the equation. I can then factor out my T final and divide both sides in parentheses. Quick thing, before I plug in numbers, let's still finish the problem, then I'll do a side tangent. But there's my equation. I'll take this equation and I will plug in my numbers, and I'll get a value. So, interesting thing. Once again, ice has a very large latent heat of fusion. And if you look at the equation, we're subtracting something. Subtracting something means T final is going to get smaller. If you put 0-degree water into your whiskey, for some reason, it's barely going to change the temperature. You put 0 degrees ice into your whiskey, it's going to super change the temperature. It's the process of melting that causes so much of a temperature change. In fact, they make the whiskey stones. They make like soapstone rocks that you've cooled in your freezer and you throw it in a drink so it won't dilute it. They will not cool a drink as much because they will not change phase. That if we do with the soapstone rocks, which there's going to be a problem on Friday where I use those, you're going to get a much, much smaller change in temperature because you want to be subtracting out this ice tone. Also, every example I've done so far had only 2 things. I sometimes put together 3 things. If you have a third thing, it doesn't make the problem any more difficult. You just have an extra term. Add another MC delta T. That if I say also there's a glass, this is the specific heat of the glass, you would just add MC delta T of the glass. I'm going to do one of those tomorrow when I go through last semester's final, because last semester I did something with 3 objects. Questions on this?
So I'm hearing that the 0-degree ice has a greater mitigating effect on the temperature than the 0-degree water, but
Yep.
I'm really not getting why.
Because if it was 0-degree water, the equation would be like that, and this term would be gone.
But why?
Because that term is just the melting of ice. If it's water, it doesn't have to melt.
Right, but if our energy change from that latent heat of fusion is, I mean, it's usually this. I mean, this looks pretty small to me. I can't do it in my head, but
well, this is 3.33 times 10 to the 5th, right?
Mm-hmm.
So the latent heat of fusion is a real big number, and it's because this number is so big that it will heavily suck out heat, cooling something very nicely.
Okay.
I say as the someone who has ice in my thing.
Okay, thank you.
No problem. It is not actually bourbon, though. I save that for when I'm not teaching. Actually, I don't like bourbon. I don't like whiskeys and bourbons at all. I don't know why I'm using bourbon. Well, actually, I do know why I'm using bourbon, because I found the specific heat of bourbon online. Let's do a small demo with this and kind of an interesting thing. I'm going to assume at some time in your life, you've probably seen these guys. That's a little thing that you kind of, the head is wet, and it'll sit there and just wait for it to go. I'm going to jump forward a tiny bit. When you first start, it goes a little slow. But you can see the liquid in there is just rising up. And what's going to happen is it's going to go. It's going to tip over. Tip over. Come on. Touch the water. Go back up. And then repeat. And this guy, as long as there's water in that beaker, will keep doing this indefinitely. That the water goes up in the neck, or the liquid goes up in the neck. It's not water. He tips over. Gets the water. Goes down. Why this works is actually everything we were just doing. How this guy works is when I first put him in the water, I get his head wet. What's going on inside there is there's kind of 2 chambers with a tube in between. The one, but most of the liquid will go to the bottom with gravity. But what happens is that beak is covered in water. And it takes energy to change water to steam. But some will happen naturally due to evaporation. That water on the beak will evaporate, but that still will pull heat. Heat can't come from anywhere. And as the water on the head evaporates, it'll take heat and pull it from the head. What this will do is it'll take heat out of the gas that fills its head But if we take heat out of the gas that fills its head, we're going to decrease its temperature. That means the head's temperature goes down. But ideal gas law, if temperature goes down, pressure goes down. The pressure is going to go down in the head. And if the pressure goes down in the head, we're going to make a suction, and we're going to suck the liquid right up to the head. If we suck the liquid right up to its head, he becomes top heavy and tips over. Though he's built in a way that when he tips over, the pressures equalize. Because the pressure is equalized, the liquid pours down to the back again. When the liquid pours down to the back again, he goes upright, but then the water will evaporate from the beak. The water will evaporate from the beak, so the temperature will go down. The water will get sucked up. He'll tip again. And he'll keep going as long as there's water on him to evaporate. And it's just because this fact that energy and phase are related to temperature. Okay? Okay, I got 4 minutes left, but I'm going to stop there because that is getting into the next topic, and it's kind of one of those things that the next topic I would not be able to get very far in it, so it seems silly to start it. But basically, what we've talked about so far is you take a hot thing, you take a cold thing, you put it together, you have a transfer of heat. What we're going to do for all of next class and, the rest of the semester, since that is next class is all that's left other than practice problems, is we're going to talk about how heat transfers, how we can transfer heat from one thing to another, the mechanisms of heat transfer. But as I said, that will be next class. So review session tomorrow, homework due Wednesday. That's about it. Have a good day, and I'll talk to you all later.